Mathias for inviting me. Is the microphone working? Yeah, good. It's such a pleasure to be in Vienna. It's such a beautiful city. I always forget how amazingly beautiful it is here, and it's so wonderful to be back at the ESI for the first time in many years. Now, so this talk here, it's the last talk, and I apologize if it's going to be hard going. I'll try to make it light. So sometimes I read expository work that Tim Gowers writes because he does a really good job, and I'm not claiming I can do such a good job of that. But this very nice thing that he does in his expository papers is that he takes some theorem from a paper, maybe one of his own theorems or from another nice paper, and he goes through it giving you just enough detail that you could actually reconstruct the proof if you took your time. It's not necessarily easy to reconstruct the proof, but you could do it, and he's very good at giving you just enough detail. And he even encourages the reader to actually not read the original research paper, try to reconstruct the proof yourself, and then you can use the paper as sort of cliff notes if you can't move past some step. So the goal of this talk is to do something similar with a theorem that I proved together with David Schroeder, and David already earlier today gave a talk that sets things up quite nicely. There's David, just in time. So he set us up nicely. So the theorem is this theorem here. So assuming ZF plus DC plus something called R unif, so that's the principle of Ramsey uniformization that David introduced. And I will need to say nothing more about it in this talk. We can prove the following: if I is an iterated Fréchet, let I be an iterated Fréchet ideal. If all sets are completely Ramsey, then there are no infinite IMAT families. And what all of this means will be explained in the talk so that you can recover the proof from the talk itself if you take your time. But I only have 30 minutes, so I ask for your understanding that things are going to be moving quite fast. But the talk is being recorded, so for those of you who actually do want to reconstruct the proof, go and see it again if it went too fast. So some background in this talk, I'll write bracket n infinity, just like David did, for the infinite subsets of the natural numbers. I'll write fin for the finite subsets of the natural numbers. That's also sometimes written like this, but I don't know that I'm using that. And a family A, which is a family of infinite subsets of the natural numbers, is an almost disjoint family. You all know this. If for any distinct x and y in A, the intersection is finite. So a mad family is maximal almost disjoint family. And in recent years, there have been lots and lots and lots of research into mad families, and especially, of course, the undefinability of mad families under various conditions. And one such theorem is the following, which now, here's a theorem where you will understand everything that it says. If all, under the assumptions of ZF plus DC plus Ramsey uniformization principle, if all sets are completely Ramsey, then there are no infinite mad families. So this is sort of a sweeping result from regularity properties to no mad families. And this talk is really about generalizing this to a situation where fin is replaced by what we call Fubini products of fin with itself. And actually, I'll only talk about the two-dimensional case because that already displays many of the features of trying to iterate the Fubini, do these Fubini products with fin with itself. So actually, and it's very easy to write down what this Fubini product, Fubini product with fin is. We call it fin squared. And what is it? It's a set of those subsets of n squared. So now we're dealing with the ideal not on the natural numbers, but on the product of the natural numbers with itself. And it's just easier to think about it like this. I'm well aware that n squared is countable, so you could move everything over to n if you wanted to. And what is it? It's those x that are subsets of n squared, so that x has finitely many infinite verticals. And you can probably imagine what a vertical is. I also sometimes call vertical columns. So you can imagine that here we have n squared, looks something like this. If you zoom out really far, it actually looks like this anyhow. And so now I have a set which has infinite, so sorry, has only finitely many infinite columns. So at some point you get to a stage where all the columns that remain are either empty or at least finite. So that's the Fubini product. And I'll keep repeating this definition a couple more times in other guises. So you already notice now that I used the boldface capital letter for a subset of n squared, and I'll stick with that. So when you see a boldface capital letter, it's a subset of n squared. I also talked about verticals, and I've tried to draw a beautiful picture of verticals. But if you want to see the definition, what is the nth vertical? It is just the set of those m, so that the pair n comma m is in your set boldface x. And so another way of writing this fin squared is just the set of those x that are subset of n squared, so that the set of those n, so that the vertical is infinite, is finite. So now that's the second time I repeated the definition of fin squared. And I hope I keep defining the same thing every time I repeat it. So you also noticed I said completely Ramsey, and many of you will know what this means, and certainly it came up many times in talks, also in Natasha's talks. So I'll just remind you. So if A is a finite subset of the natural numbers, and capital A is just some subset of the natural numbers, then A in this square inclusion means that little a is an initial segment of the set capital A. And when little a is an initial segment of capital A and capital A is infinite, then we will define square bracket AA to be the set of those B, and it should say the natural numbers here. So it's those infinite subsets of the natural numbers, so that A is an initial segment of B and B is a subset of A. And this is what is known as an Ellentuck open neighborhood. Again, Natasha's talks and other talks, this has been discussed. And note, of course, that if I just take the empty set as my initial segment, then say bracket empty A is just the infinite subsets of capital A. And now finally, the important definition that you hopefully know, or maybe know, but if you don't, here it is. So if S is a collection of infinite subsets of the natural numbers, then we say that S is completely Ramsey. If for every finite subset of A of the natural numbers and every infinite A, where little a is an initial segment of capital A, there is some infinite set B which is a subset of A and has little a, lowercase a, as an initial segment, so that this Ellentuck neighborhood is either contained in our S, or it is disjoint from S. So this is a well-known definition of completely Ramsey, and now you've seen it, and with all these definitions, I claim you can reconstruct every proof from these slides. So let's, so now I want to state the theorem that we're really interested in. So let me just say, so if let I be an ideal on the natural numbers or on some other countable set, such as n squared and so forth, a family A is called I disjoint if for any distinct X and Y and A, we have that the intersection is an I. So traditional mad families would just be the case where I is fin. An I disjoint family is an I mad family or a mid family. And we always think this is funny until we always end up writing this instead and saying this. So I mad family, if it is a maximal I disjoint family. And an iterated Frechet ideal is an ideal that arises as a finite or infinite iteration of the Fubini product operation starting with fin. And so for the third time, here's the definition of fin, Fubini product fin. And I'm of course writing this down appealing to your intuition that if I can do one Fubini product, I can iterate this. And you can iterate it even finitely, but I'm not going to do that in this talk. So here it is again. This is the Fubini product of fin with itself. So that's fin square. And now I've said everything I need to say. So here is the theorem. This is the theorem that we're really interested in. let I be an iterated Frechet ideal. I said this already at the first slide, but this is the theorem we're trying to prove. So let I be an iterated Frechet ideal. If all sets are completely Ramsey, then there are no I mad families. And of course, now I'm happily identifying n squared or n to power k or something like that with natural numbers, so it fits this definition. But in particular, if all sets are Ramsey, then there are no fin square mad families. And that I'm now sort of getting to what I'm really going to show you in this talk because I keep saying fin square rather than iterating further, and that's because I want to present a proof. So what we're really doing in this talk is actually we are providing a proof of the following theorem, which I proved together with my PhD student Karen Bakke-Hauger and David Schritter a number of years ago, that there are no infinite analytic fin square mat families. And this is really what I'll show you, but I'll give you a proof that is Ramsey theoretic, as opposed to the proof that we did back then. So I'll sketch a proof based on a Ramsey theoretic approach, developed to prove this much more general theorem on the previous slide. And the original proof is as I said, it is actually a proof that uses forcing and absoluteness just to prove this statement about analytic sets, really. So it used a lot of power. And this is a little bit simpler, I suppose. And since I'm working in the analytic case, you'll have noticed that the assumption, it's probably good to work in ZF. I'll be doing that. And DC, you can probably get away with not assuming because I'm just dealing with analytic sets, and whenever I need to make some choices, I anyhow can do that. But what you'll notice is gone from here is also the R-unif, the Ramsey uniformization principle. That is gone too. And why is that gone? That's simply because if I'm working with in the analytic case, when I need to uniformize things, I have a theorem. I have the Yankov von Neumann uniformization theorem that just will let me not in a REL measurable way, but in a sigma of sigma 1,1 measurable way, or sigma of analytic sets measurable way, pick or uniformize things. And since I can, so that means I can actually uniformize things in a way that is measurable with respect to the Ellentuck topology. And therefore, I don't need Ramsey uniformization. So I've edited some important ingredient of the general theorem out by going to the analytic case. But I still claim that this is actually highlights most of the interesting ideas of the proof. So anyhow, for the remainder of the talk, I'll now fix A, which is a subset of the power set of n cross n, which is an infinite analytic fin square almost disjoint family. And eventually, a number of slides from now, I'll have proven, or at least sketched, a proof that this is not maximal. Now, one of the things that we have to do here is we have to move from one dimension, because Ellentuck's theorem and the Ramsey property and so on, so stated so far, is something about collections of subsets of the natural numbers. And I want to prove something about a certain family of subsets of n squared, of natural numbers cross itself. So I want to move from one dimension to two dimensions somehow. And the key idea behind this Ramsey theoretic approach to this theorem is that there's a certain operator, the tilde operator, which allows us to take a set, an infinite subset of the natural numbers, and associate to it a set tilde A, which is actually in fin square plus. So now I didn't use a boldface letter here, but that was because it was starting to get ridiculous with having a tilde and a boldface. But anyhow, so I'm moving from a subset A, which is a subset of the natural numbers, to some tilde A, which is a subset of n square. I might write down that here, that A tilde is a subset of n square. So I'm moving up the dimensions. And not only that, I'm from an infinite set here, I'm getting a set which is in fin square plus. And what is fin square plus? I'm not sure I said that on any slide. Fin square plus is the co-ideal of fin square, the positive sets. So these are the things where there are infinitely many places in which there is an infinite column or vertical. So recall that A is our fixed infinite fin square AD family. And I'll make, again, small simplifying assumption. And that is that we suppose that we have a sequence ZL of elements of A, such that all non-empty columns, or verticals, if you like, of ZL, each of those ZLs are infinite. If this is a small modification of countably many elements I've picked from my family, there could be some finite columns, but then I've just modify the family so the finite columns become empty. And I'll also arrange by diagonalization argument that if L is not equal to M, then ZL intersected with ZM is actually empty. And again, you can sort of massage your sequence to arrange this and make a small modification of your family if you don't already have this. And now we're almost at the definition of that famous tilde operator that I've been advertising. Because I denote, and now just hang on here. So I might illustrate on my beautiful, beautiful picture. So I'll denote by Z hat L Mn, the nth element of the mth infinite column of ZL. Now I said all the columns of ZL are infinite, so I didn't need to say that again, but why not? So what are we doing here? We're the nth element of the mth infinite column. So what I'm doing is that I'm walking out to this, this would be the third infinite column of ZL. So this beautiful picture is of ZL. So I walk out here, so say M is equal to 3. I walk out to this point here. And then I start going up to the nth element of this infinite vertical. And that's what I'm doing. And here's the tilde operator. So from a set A, so if I have, and I guess I didn't say that anywhere, I wanted to fit the whole definition on one line. So I ended up not saying what A is, but A is an infinite subset of the natural numbers. And to this A, I associate my A tilde. And what does it do? Well, it looks at Z hat LMN, so that is the nth element of the mth column. And it puts that into A tilde if, well, first of all, that L, M, and N has to be an A, the one-dimensional set I'm transforming to a two-dimensional set. And L has to be less than M, which has to be less than N. And then, importantly, L and M are consecutive in the infinite set A. So if I have A over here, there were such beautiful illustrations in Tasha's talk of how these things work. And I'm almost like an artist on the blackboard, as you can see. So what I'm saying here is I have to take L and M that are consecutive. And then after that, the N has to range inside of A. So this set that I've drawn here is A as a subset of the natural numbers. You can see there's some gaps in between here that might not be in A. So now it's quite easy to show that tilde A is actually in fin square plus, that you get infinitely many infinite columns or verticals. And this is the operator. And here comes the theorem. And this is really the heart of what we're doing here. And I think this is, this is almost startling when you read this, because what is it saying? Mind you, I've reduced to a case where we only have an analytic fin square almost disjoint family, but still it's saying the set of those A infinite subsets of N, so those A that are infinite subsets of N, so that tilde A is fin square almost disjoint from every X in our family, in our fin square almost disjoint family A, is Ramsey co-null. And so A is certainly not maximal, because if you were generically in the Ellentuck topology picking some A and then forming A tilde, you would have an element which does not intersect any with A, which is fin square almost disjoint from every X in A. So I mean, so what this is saying is that if you're blindly in the Ellentuck topology picking a generic element, then the A tilde will be something that shows that this script A is not a maximal fin square almost disjoint family. And this seems quite startling. You can't fail to see that such a family is not maximal. Now here, so David said something that is interesting, and that was that he said sometimes he wakes up at night and he thinks, how can this trick of moving from one dimension to two dimensions, how can it really work? Would you not expect that you needed some kind of two-dimensional Ramsey theorem? Would you not need Natasha's Ramsey spaces that arise from actually a sort of Fubini iteration thing? Would you not need that? And if I were to ever wake up at night with such thoughts, and I don't, I sleep very well in general, I would look at this list of important facts about the tilde operator. The first fact about the tilde operator is, so I'll fix some x, which is a subset of n, so that if ever you see a capital X down here, that's because it was this one up here. But the first one just says that states something we call fin square equivariance, and that says that if A symmetric difference A prime is in fin, so if A and A prime only differ on a finite set, then actually A tilde and A tilde prime differ only on a fin square set. So small changes to A result in small changes to A prime. Oh, sorry, A tilde. This we called fin square equivariance. And if some of you are doing this kind of descriptive set theory with lots of group actions and things, you're very, very used to the idea that there's equivariance happening with maps. If you're not doing that kind of thing, there's the definition. And I think this is why we should not wake up at night and be scared and think that the theorem is missing something. It's not, because there are two pigeonhole principles, and these are really the driver of. This is why the tilde operator is so right for the job. First is the domain pigeonhole principle. And now I did say this in advance to Vera. I had forgotten to define what the domain is, but the domain of some x, so if x, oh, I shouldn't use x because that means something else there. So what will we use? Yeah, the domain of B tilde, thank you, is simply, domain. B tilde is simply those n in n, so that vertical is non-empty. That's all it is. So pigeonhole principle for the domains for any, so for any Ellentuck open neighborhood A, A, there is a B in A, A, so that either the domain of B tilde is almost disjoint from this fixed X I had here, or the domain of B tilde is almost contained in X. So either you choose, you can generically choose to either have your domain avoid this X, or you can have your domain essentially go into this X. And pigeonhole principle for the verticals, or columns, if you like that word better, for any Ellentuck open neighborhood, and for any M which is in the domain of A tilde, there's a B in the Ellentuck neighborhood, so that M is in the domain of B tilde, sorry, apologies. And either B tilde of M, the mth vertical of B tilde intersected with X is finite, or B tilde of M is almost contained in X. So what I said about the domains could choose to either go into some fixed X or avoid it. You can do the same for columns. You can choose at a column, the tilde operator can select whether to avoid something, accept or reject something really in the columns. And these two pigeonhole principles really drive the whole thing. And I have to watch the time a little bit. Then there's the almost disjointness principle, and that says that for any A in our family and any Ellentuck open neighborhood, there is a B in our Ellentuck open neighborhood so that B tilde is intersected with A is in fin square. So if you're just trying to avoid one element in your fin square almost disjoint family, you can do that generically. That's what this is saying. If I couldn't avoid one element generically, I couldn't avoid the whole family generically. So this, without this, I would not have been very optimistic. So now, we'll prove the genericity theorem that proves the whole thing. And perhaps seeing that time is running, this here slide really just is saying something that you all know. I can get a tree representation of an analytic set. So in the interest of time, I'm just going to say there's a tree representation of analytic sets. And you've all seen this. And I can choose one that's very suitable for the job by looking at 2 to the n cross n, which is kind of Cantor space, really. So I can fix a tree representation. And this is being recorded. So if you want to see the tree representation I suggested, you can look that up. And so I have fixed an infinite analytic fin square almost disjoint family A and a tree T such that the projection of that tree is A. And we'll write T sub T for the tree of those things in T that are compatible with T. So T sub T is those S and T so that S is compatible with this T. And then we make the following definition. We say if I have X, which is a subset of n squared, and I have some D, which is a finite subset of the natural numbers. But first, I just define Tx to be those T and T, so that there is something in the family. Oh, sorry, this script A should not be there. That should be deleted. So there is some A in the projection of the local tree TT, so that A intersected with X is in fin square plus. And then TXD should be that there is, I wrote that down. No, same, I copied that over, obviously. So the T in T, so that there is something in the projection of the local part of the tree, so that it hits my X in a fin square plus set, in a positive fin square positive set. And for all I and D, the intersection of the verticals AI and XI are infinite. So this tree here, if I took D to be equal to the empty set, I'd just get TX, the first remark. But the way to think about this TXD is it's the tree of attempts at finding some A in our family so that A intersected with X is big. It's the tree of attempts at showing that actually this particular X is not avoiding the family. So I have repeated the definition with all the misprints here. And the key thing about this definition is it has nice invariance properties. If if the symmetric difference between X and X prime is in fin square and is in our ideal, then the tree doesn't change. And it has a conditional invariance, namely that if X and X prime if there are symmetric differences in fin square, and additionally, all the verticals have symmetric differences that are finite, then the tree here doesn't change. And this, again, if you're doing sort of descriptive set theory with groups and actions and things, this is quite a familiar thing. Try to look for invariance properties. And it's actually obvious from the definitions, but I'll let you check that if you want to. So now I have 1 minute left. So the ambition to run through the proof has slightly failed. So I'll try to wrap up here. So for any A, for any A, which is an infinite subset of natural numbers, there is a B, which is a subset of A, an infinite subset of B of A, infinite set B, which is a subset of A, such that for every X, which is an infinite subset of B, and for every D, which is in the domain of X tilde, we have that Tx tilde D is equal to T B tilde D. So what is this saying? This is saying that actually inside of any infinite subset of the natural numbers, I can find a B where all of these functions that sends the corresponding TXD, since this over, now it's warning me that I'm out of time. I do this when I teach my calculus students. You get very, very angry at me if I go over time, and then they give me bad evaluations, and then you know the rest of the story. You have to explain that to someone. So anyhow, so very quickly. So what I'm saying here is that inside of any capital A, I can actually find a B so that this tree is stabilized. It never changes, becomes constant. And you can imagine the proof. The proof is just that this function here is Baire measurable with respect to the Ellentuck topology. So now you just accept or reject T or D all the way until you accepted or rejected everything. And then the rest of it. So now I'm really out of time. So this is it. Now I have a problem. So there's a lemma that we will skip very quickly but the key point is that once you've stabilized this, you will be able to prove two things. You'll be able to prove that if the projection of this tree TA has one branch and no branches, then it has no branches. So it has one element, then it has actually the tree is empty and it has no branches. And that leaves us with a situation where if that the projection of this tree, the stabilized tree, has more than one branch, and then we can use this pigeonhole principle to construct a way of splitting up our A so that actually it gets rid of one of those at least two branches, and everything collapses because you had made a promise to keep these two different things in your tree, and you had stabilized that, and now you're saying, no, I can get rid of one of them, and it all falls apart. So I apologize, I have to rush through the rest of it, but you can get my slides, and the paper is online if you'd rather read that, but you can get my slides. So thank you for listening, and I just want to say there is an appendix on the last slide with the proof that was not in the slides. So if you're trying to reconstruct the whole proof, you probably want a few hints to one of the lemmas that I skipped over so fast that you're all completely lost anyhow. So thank you very much.